Greetings, everyone. Welcome back into trigonometry. I want to take a sidestep for a minute and just talk about a test that I usually give in my class. And the goal here is to just give you an idea of the types of questions that can be asked at this point in the course. However, as with all of the tests, I'll repeat and say this, I want to emphasize that to study in a math course, to study math skills, you should not memorize problem types. You shouldn't memorize specific problems. You should focus on the methods and the skills and the organization of those skills themselves. If you focus too much on individual problems, you'll miss the forest for the trees. In other words, you won't get the actual idea behind the math, and you won't carry it on with you. And remember, the main goal here is to carry these math skills with you in case you need to do another math class after this, or if there's another problem solving course that requires these particular skills. Okay, so focus on each of the individual methods and how I'm approaching them in general, not the individual questions. Okay, so the first test in trigonometry in the courses that I teach cover angle measure, which is basically what is an angle. You have to be able to, find a particular angle measure given a point on a grid or something like that. And then, of course, the two different measurement systems, degrees and radians. Arc applications are anything dealing with arc length or, say, sector area or those are the two main ones. Rotational velocities, anything where it's rotation to straight line measurement like that is considered like an arc application. Basic trig operations is using sine, cosine, tangent, secant, cosecant, cotangent in right triangles with acute angles. That's the basic trig operation. So we're talking about a free floating triangle, maybe an application of some sort. And then that's where it comes into solving with right triangles, finding missing measurements when you know some information in a right triangle formation. And then you expand into trig operations for any angle. So we're talking about things that may not fit inside of right triangles. We're talking about finding things on the actual Cartesian plane in other quadrants other than quadrant 1, including quadrant 1. And then also basic trig identities, the Pythagorean identities, the quotient identities, the reciprocal identities, and the cofunction identities. Okay? Any of these topics seem somewhat foreign to you, I urge you before you watch this video to go back to the videos before this that actually talk about these particular skills, and then come back and when you're watching this video, see if you can pause me before I actually work the problem and see if you can work it, because that's the design of this video, is to give you that extra set of examples, but also an extra little oomph for yourself to see, can I work these as well. Okay, so let's begin with a problem dealing with identities. Using only the identities, the basic identities, calculate the other 5 values for some specified angle. And usually when we say specified angle, it's because you're given some sort of information about that angle. So notice here it says tangent of theta, theta being the angle, right, is equal to negative 14/5. And theta is an element or exists in quadrant 4. Okay, so this would fall in the category of the trigonometry of the non-right angles, right, of the broader trigonometry of all angles, because we're in quadrant 4. This is a bigger than obtuse, if you want to think of it that way, angle. Okay, so and I want to point out one other special thing here. It says using only identities. There are actually 2 ways to work this. One method I call the ACT method is actually a lot quicker and more efficient. But the point of this problem is not efficiency. The point of this particular problem, when it's asked of you, is to see how you are doing with understanding formula and identity manipulation. Okay? Which is a very useful skill, an important skill for people who need trigonometry in this course and in courses that are subsequent to this one. Okay, so let me show you first the method that you should not do. The method that I should not do is draw it out and actually make a right triangle in the quadrant with a reference angle. Okay, so this right here is what we are not supposed to do. Do not draw out the angle. It says quadrant 4, so that means that my angle, is something like this. This would be theta here, which of course means that I would form a right triangle with the reference angle here. Now, I don't know what the reference angle is, just like I don't know actually what theta is, and we don't care. Okay? What I'm not supposed to do is draw this out and make a right triangle out of this. Okay? But since the tangent of theta is negative 14/5, of course you would then label the sides of what you're not supposed to do, right? And I'm showing you this in case you ever, doing this on some other test besides this one. Negative 14 would be here, and 5 would be here, because tangent is opposite over adjacent. And then, of course, you could find the hypotenuse here using Pythagorean Theorem, right? So if I label this C squared is equal to 5 squared plus negative 14 squared, and so on, right? You could actually figure out what C is, and then I could set up whatever trig ratio I want, because I've got all three sides of the right triangle formed by that angle, right? Do not do this method in this problem, okay? That method is very efficient, but it is not the one asked for. It specifically says using only identities. So that's what we're going to do now, okay? Here's the actual way to work this problem. I notice that I have tangent, okay? The first thing that comes to mind is, well, tangent is the reciprocal of something, right? And it wants all 5 of the other operations. So that's going to be sine, cosine, secant, cosecant, and cotangent that are missing. I have tangent of theta, but I need all those other ones of theta as well. Okay? So immediately, I think reciprocal, right? The reciprocal identity of tangent gives me cotangent. And I'm just reciprocating. Negative 5 over 14. And I've already got one of the 5 that they asked about. Okay? So that, pretty straightforward there. Not too difficult on that one. Let's continue. In all of these operations, you're going to find yourself having to do something with some squares, right? If you did it in this method, the squares come up in the Pythagorean Theorem. Much like if you're going to do it with the identities, they would come up with the Pythagorean identities. So tangent, since it's the original, I'm going to go ahead and go with that one. I know that my tangent is related to secant with the Pythagorean identity, right? Tangent squared of theta plus 1 is equal to secant squared of the same theta. Okay, so I'm going to use this identity and the fact that I know what tangent theta is. So I'm going to get negative 14/5 squared plus 1 is equal to secant squared theta. And then, of course, right here, 14/5 squared is going to give me 196 over 25. Square root of a negative is positive, so I'm not worried about the negative. Instead of writing 1, I know that I'm going to have to interact some fractions here, so I'm just going to write 25 over 25 so that I can have a common denominator. And this is still equal to secant squared theta. Okay, then, from here, I add these two together, right? 196 plus 25, and it's going to be over 25, and it's still equal to secant squared there. So that's going to give me 221 over 25. And now I simply am going to take the square root, right? To get rid of the squared on secant squared here, I'm going to square root both sides. So I'm going to be doing the square root of 221 over 25 is equal to secant theta. And here's another thing. Plus or minus, right? Should be a question here. Whenever you bring up the radical, it's which one is it? Well, that's very important here too, because the quadrant that we're in could give a positive or a negative. It's not quadrant 1. So let's think about it for a second. Quadrant 4. Well, remember, all students take crap, right? Or all students take calculus, whichever one you're using to remember. We're in quadrant 4, which is the cosine is positive quadrant, right? Quadrant 4, right, along with this piece of information, and that's important, right? I had to have that to make this decision. I have to remember that cosine theta is a positive number, right? Or actually the true way to write that, cosine theta is greater than or equal to 0. Strictly on the greater than, because we're not actually on a quadrantal there, right? So I'll just go ahead and put greater than. I know that cosine is positive. Okay. Well, I'm not looking for cosine right now, am I? Well, not directly, but it is one of the 5. Okay. And secant is the reciprocal of cosine. Well, if cosine is going to be positive and secant is his reciprocal, right? We're just flipping fractions there. That means secant has to be positive also. So right here for my decision, I'm just going to leave it positive. And that will resolve the information here. That will be the correct solution there. Okay, now I'm just going to simplify this radical here. 221 is not divisible by 3. It's not divisible by 9. Let's see, is it divisible by 7? No. Okay, so then what I have is the square root of 221, and it's just over 5 is equal to secant theta, right? Okay, so I've got now one more of the answers. And again, take hold of a reciprocal identity, right? Reciprocal of secant is cosine, which is going to give me 5 over the square root of 221. And of course, in some courses, your teachers may not want you to have the radical in the denominator. So of course, you're going to fix that by multiplying top and bottom by the radical, in which case our cosine theta would be equal to 5 square root of 221 over 221. Right? Let's double check something here. Okay. So now I've got how many? 1, 2, 3, 4 out of the 6. Right? I've found cosine and secant. I have tangent and cotangent. The only two now missing are sine and cosecant. Okay? Well, I've used a couple of different sets of identities already, right? I've used reciprocal. I've used Pythagorean. Well, there's one more. I could use Pythagorean again, right? because I could link cotangent to cosecant. And if you want to do that, that's great. All right, that would be a perfectly good way to do it. You'd go through the same kind of thing as this, but cotangent would relate to cosecant, and then of course cosecant would reciprocate to sine. However, I want to use a different pair so that you can see this other identity in action as well as a good example. Okay, we could also use our quotient identity to find sine theta because I know two of the other pieces in it. So this is what I mean. Remember that tangent theta is equal to sine theta divided by cosine theta. And I can manipulate this identity, right? This is our quotient identity here. I can manipulate it. Since it's already a proven identity, I can put it into different formats using multiplication, division, whatever. I'm just going to multiply both sides by cosine theta. So I have tangent theta times cosine theta is equal to sine theta. Now that's actually a pretty interesting and useful alternate version of that quotient identity. It no longer is really a quotient, right? Because it's not doing this quotient here. But I happen to already have tangent and cosine of the theta. So I can go directly to calculating sine. My sine theta is going to be equal to tangent, which is negative 14/5, times cosine, which is 5 square root of 221 over 221. And notice the 5's can eliminate here, leaving me with sine theta is equal to negative 14 square root of 221 over 221. Now 221 is 13 times 17, so nothing's still going to reduce from that one. And I now have sine. Here's another thing to note. Sine is already negative just from this multiplication. And it's supposed to be, right? Cosine and secant are the only ones that are going to be positive in this quadrant. Sine is negative, as it should be. It was already taken care of because of the way the tangent was set up and because the cosine was positive from our decision, right? So once you make this decision, I decided to leave it positive here. That should trickle down to everything else that flows from that. Excuse me, one calculation left. We just need cosecant. Cosecant being the reciprocal of this. Now, side note, don't forget that an alternate version of this tells me that sine theta could also be written as negative 14 over the square root of 221. Right? This is what we call the fixed version, right? The rationalized version. But for interests of the reciprocal, I'm going to go ahead and write it in the non-desirable format real quick. And to do cosecant, I'm just going to reciprocate it. Cosecant of theta is going to be negative square root of 221 over 14. Now let's look at some problems that test the basic organization and usage of the terminology of a lot of the trigonometry inside of the whole Cartesian plane in any quadrant, trigonometry of any quadrant type of topics here. Okay, so some of the terminology is going to be really important when you're reading a problem that's nothing but words and they're trying to describe something to you, right? So standard position is an important terminology. Knowing that standard position means an angle that's starting on the positive x-axis and rotating counterclockwise according to the right-hand rule, if it's positive, right? And then clockwise if it's negative. But A is a standard position angle, meaning if they don't say it's a negative angle, they mean it's a positive angle. Okay? And then they're telling you that a point is on the terminal side. There's another key term, right? The terminal side of the angle has this point on it. So you can imagine the side of the angle, right, rotating around. and you have this point located where the side that's rotating stops. They want you to calculate the secant of angle A. Okay, so let's start by drawing it out. We're going to draw angle A here. So angle A is going to have 15 and negative 20 on its terminal side. Well, 15 and negative 20 is in quadrant 4. So I'm going to draw the terminal side in quadrant 4 here. And then the point is here. We'll just label that 15 comma negative 20. Right? Is that point right here on the terminal side. The angle itself doesn't necessarily have to be drawn through that point, but the angle is going to be in standard position. So here's angle A. Okay? Now, of course, angle A is going to have a reference angle in here, but we don't really care about the measurements of the angles right now because it doesn't want us to give the angles. It wants me to give the secant of angle A. And that's what we're going to compute. So then I imagine using the reference angle here, I'm going to have a right triangle here, right, using the terminal side. And this right triangle is going to be something, let me put the point here at the end. Let's say that the point is here instead. Okay, so if the point is here, then I already know the opposite and adjacent sides. This is going to be negative 20. This is going to be 15. And secant of an angle is defined as the hypotenuse divided by the adjacent. So I just need to find the hypotenuse, put it over the adjacent, and reduce. Okay, so then I'm just going to use a little bit of my knowledge of triangles here. This is a 15, 20, 25 triangle. Mr. Simon, how do you know that 15, 20, 25 is correct? Because there's a famous 3, 4, 5 triangle. And this one is just similar to that one, right? Because notice 3 times 5, 4 times 5, that would be 5 times 5. Okay? Or use Pythagorean identities, Pythagorean theorem if you want. 15 squared is 225. 20 squared, right, it's 400. Add those two together, you get 625, which is 25 squared. It is a Pythagorean triple. Okay, so here, now that I know the hypotenuse is 25, the secant is just going to be 25 over 15. Which, of course, we would want to reduce. And there's my answer for that one. Okay, so mostly terminology for that one and understanding the meaning of those words and how they appropriate a way to set up the problem itself. Next is something very similar. Again, it's in the terms and then some of the basic identities. Rewrite this operation in terms of its co-function. Now remember, every trig operation has a co-function operation. Hence with the whole co-naming system, we have sine and cosine, secant and cosecant, tangent and cotangent. Right? And remember, the co means complementary. That's the whole purpose for having the co in front of it, because it means the complementary version of that. Sine and complementary sine, secant and complementary secant, tangent, complementary tangent. And complementary is implying that the two angles should sum to 90. Okay? Therefore, this, I'm just going to write the co-function. Co-function of cosine is sine. And then the angle here can't be the same. It would be the complementary angle, right? So then if I were to do 90 degrees minus 37.8 degrees, right? 90 minus 40 would be 50, and then that would be 2 and 2, right? So 52.2 degrees. Right? And that's the answer for that one. Literally, we just rewrote it in terms of its co-function. And anytime you switch a function to its cofunction, you switch the angle to its complement, right? So that's that one. Okay, and then basically an extension off of that first problem is finding an exact value for a sine, cosine, or tangent, or secant, or cosecant, or cotangent, whatever, of just some angle if it's a basis on our main memorized angles. Okay, so here I've got the sine of 2,730 degrees. So I start out by trying to section this out into where does this land in the four quadrants, right? And then I also want a reference angle. So the problem specifically asks for the graph and the reference angle, but you're going to do that anyway. You really need to show the understanding and to show make sure that you're in the right place and setting up the right problem. Okay, so here's the easy way to do these kind of things. Obviously, way more than a single rotation, right? It's going to be several rotations. It's 2,000, almost 3,000 degrees of rotation, where it only takes 360 degrees of rotation to go around. Okay, so here's what I do. I take the 2,730 and I divide by 360, like so. Once I do this division, it tells me 7.58 and then a continuous 3. Well, think about this for a second. I divided it, okay? And I got 7 point blah, blah, blah. What that means is that there are 7 full rotations and then some more, okay? So I can already start graphing this thing. Here's what I mean. For 2,730 degrees, I can start graphing this thing by showing that there are 7 full rotations. So 1, 2, 3, 4, 5, 6, 7 full rotations. And notice I stopped on the x-axis there because that's the 7 full fullest rotation. The 7 full rotation stops there. So here's what I do on the calculator. I say minus 7. So all I'm left with is the decimal. Then times 360. After you multiply by 360, you notice you get 210. So what does that mean? After I subtracted off the 7 full rotations, the part that was left over was 210 degrees. I subtracted 7 full rotations that I re-multiplied by 360 so that I could see what part of 360 it was 210 degrees. Well, I know that 210 degrees is in quadrant 3. So, therefore, I'm going to be doing a quadrant 3 angle. And for the rest of my rotation here, right, is just the extra 210. So just this portion right here was 210 degrees, okay? But the full rotation, all of this, here, 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 all of that was the 2,730 degrees, right? Going all the way around. The blue part right here, that's 210 degrees. And then the part that I'm really interested in, the reference angle, right? Now that I know this part right here, I know that's 180 degrees, okay? So then my reference angle is just this piece right here. My reference angle, I'll just put ref, is equal to 210 minus 180, 30 degrees. So those are the two things that the instructions are asking for. The angle is graphed, and I have labeled a reference angle. I can answer the question now. The sine of 2,730 degrees is equal to the sine of 210 degrees. This is one of your identities. It's always true if two things are coterminal. Okay, the 2,730 is coterminal with 210 degrees. It's also coterminal with however many other times it goes through that thing. But the 210 is the one I'm concerned with. Since 210 is in quadrant 3, I know that this is going to be a negative answer. And then I just need to know the size. Well, the sine of 30 degrees is 1/2. So there's my final answer. Okay, next, 240 degrees. Very similar idea here. 240 is less than a full circle though, so I don't need to divide it out or anything. I know 240 degrees is also in quadrant 3, like so. So I will graph the 240 degrees, like so. And then I'm going to compute the reference angle, right? That's just going to be this guy right here. This angle right here, my reference, is 60 degrees because it's 240 minus 180. Okay? Now, next, I need to know what the cosecant of 60 degrees is. Well, I know that the sine of 60 degrees, right? That's one of our memorized angles. That's square root of 3 over 2. Okay, so well, what about cosecant? Well, then that means that the cosecant of 60 is 2 over the square root of 3, because sine and cosecant are reciprocal operations, which of course I will fix to square root of 3 over 3. Now that's the cosecant of 60 degrees. That's my reference angle. That's the size. Now the sine, however, right, is negative in quadrant 3. So the cosecant of 240 degrees is negative 2 square root of 3 over 3. Okay. Lastly, I have the tangent of negative 5 pi over 6. Now that's a negative angle, which means I'm going to rotate clockwise. And 5 pi over 6, I know is going to, again, land me in quadrant 3, but negatively. Okay? How do you know that? Well, 5 over 6 is less than 1. And pi, 1 pi, is exactly half of a rotation in radians. So I know to graph this one out, it's going to be something like this. And my negative 5 pi over 6 is going to be this rotation here. Okay? And remember, this is pi over here on the axis. So as far as size is concerned, if I do pi minus 5 pi over 6, then the reference angle is just pi over 6. This angle here is just, my reference angle is pi over 6. Remember, reference angles are always drawn to the x-axis, right? I always draw them up with the x-axis. Okay? So pi minus 5, or 1 minus 5, 6 is 1/6, but with pi's. So I have pi over 6. Okay? Well, remember, pi over 6 is the same as 30 degrees. And we're trying to do tangent here. Okay? So what would the tangent of pi over 6 be? Well, that's the tangent of 30 degrees. That's square root of 3 over 3. So then the tangent of negative 5 pi over 6, well, we're in quadrant 3. Remember, in quadrant 3, all students take. Oh, that's the t quadrant. That's tangent. The tangent should be positive, even though the angle is negative. I'm in quadrant 3. Therefore, I have a positive answer over here. And the reference angle is pi over 6. So this is just square root of 3 over 3. Positive. Okay, so those last three are based off of knowing the memorized angles, right? The 30, 60, 45 type angles, the 0, 90 ones as well. Okay, and then also understanding how to throw out the reference angles on these things. Here's a problem that's very similar to those last three that we did. It's basically just the reverse. So this one relies heavily on you knowing your memorized angles and which ones go with which ratios. Find two solutions for theta that are in between 0 and 2 pi. Right? So in other words, in one cycle, not coterminal, not like many rotations. Less than a full rotation, there are exactly two solutions for most basic equations. Okay? So this is actually a trigonometric equation. We haven't actually gotten to solving the major equations yet, but this one you can do because you're supposed to know the certain angles and their special values. Okay, so here what I do is I look first at the relationship of the trig function with the SIGN, tangent with negative. I know that tangent is negative in quadrant 2 and quadrant 4. That's a huge piece of information right there. And that's going to show us why we're getting exactly two solutions. I should be getting a solution for an angle theta in quadrant 2 and an angle theta in quadrant 4. Okay, so I'm going to draw those out. I should be getting a quadrant 2 answer, right? Theta's here. Or I should be getting a quadrant 4 answer. Theta would be here. Okay, next piece of information is how does the trig operation match up with the ratio? Which angle from the memorized bunch has a tangent of square root of 3 over 3? Okay, well, that's going to give us the reference angle that we need. This tells me that my reference angle must be 30 degrees because the tangent of 30 degrees is square root of 3 over 3. However, they want it in radians, 0 to 2 pi. So I swap over. 30 degrees is pi over 6. Okay, so now what this is telling me is that the pi over 6 for quadrant 2 should fit here, right? This should be pi over 6 right here. Well, that means that theta in this particular setup here is going to be equal to pi minus pi over 6, right? Because this is pi right here. And pi minus pi over 6 is 5 pi over 6. So there's one of the two answers right there. Next, in quadrant 4, my reference angle has to be here because it's going to be drawn to the x-axis. And that's supposed to be pi over 6. And remember, in a full rotation, this axis right here represents 2 pi. Well, it also represents 0, but since I'm going all the way around, it's 2 pi. Which means, in this case, my theta is going to be 2 pi minus pi over 6. Right? So 2 pi is 12 over 6, 12 pi over 6, minus 1 pi over 6. So theta is 11 pi over 6. If you also wanted to do these in degrees first, note that that would also work, and then you could just convert later, right? Right here, you would get 150 degrees, which is 5 times 30, 5 pi over 6. And over here, 360 minus the 30 would give you 330, which is 11 times 30, or 11 pi over 6. Okay, so whatever way you want to do it first, these are the two answers that you should get any which way. Now it's time to finish up with all of the application problems that deal with either angles or triangles and things like that. Here are two arc applications using angle terminology, right? So Julie measures the outer edge of a slice of pizza to be 9 inches and the length along the side to be 7 inches. And they want us to find the area of the surface on top of the slice of pizza. So if you think about a slice of pizza, remember that it, cut normally, not the square kind, right? The angular kind of cut. The slice of pizza should look, like this. Where, the rest of the pizza is, I'm terrible at drawing this. Right? It should be the slice cut out of the pizza. So there should be an angle here. We'll just call it theta. And basically the slice of pizza is a sector of the circle, which is the whole pizza. And what they're telling us is that she measured along the side to be 7 inches, right? So that's from here to here, which would be the radius of the sector, all right? Which would be the radius of the whole circle too. And then the 9 inches, now of course this isn't drawn to scale because obviously I'm a little bit off here, but it should be 9 inches along the outer edge. And that's an arc length, right? So the 7 inches is the radius. And then they want us to find the area inside of here. Okay, so there's two formulas that are in play here. First of all, how does arc length relate to radius? Right? We know that arc length symbolized with S, right? That's arc length is S. Radius, I'll use capital R. S is equal to theta times R, as long as theta is in radians. Well, I also know that the area that I'm looking for, right, area, is equal to 1/2 theta r squared, right? That's the formula for the area of a sector. Well, I need a theta and I need a radius. I have the radius measurement. I don't know a theta, but I do know an arc length, and using the radius and an arc length, I can define an angle in radians. So right here, note, theta is going to be equal to the arc length divided by the radius. In this case, 9 inches divided by 7 inches. So 9/7 is my theta in radians. Okay? So it's actually a really nice way to be able to define angles using a ratio of two, pretty straight measurements. Even though the arc isn't technically straight, you could bend a tape measure around the outer edge of pizza if you were, that bored at a pizza place. You could do that. Not saying I have. Area then is equal to 1/2. Theta is 9/7, and my radius is 7 inches squared. Okay, now notice the units. Theta, being in radians, is unitless. This is inches divided by inches, no units. And then r is in inches, but it's squared, which should give you square inches. And that's exactly what area should be measured in. Okay? Next, notice I've got 1/2, and then 9, and then I've got 7, and then one of these 7s is going to wipe out with one of those. So what I ultimately end up with is 9 times 7, 63/2, right? Or 31.5 square inches. Okay? Next application here, a car with wheels of radius 12 inches is traveling forward, and of course traveling, the wheels have to turn, right? Causing the wheels to turn at 23 revolutions per second. we would like to know how fast the car is moving forward in miles per hour. Okay, so there's a couple of different ways you could approach this. Personally, I think of this as just a unit conversion problem. There are all kinds of formulas for converting angular speed into linear speed, or vice versa, linear speed into angular speed, right? They'll usually say something like v is equal to omega r, right? Where v is the linear velocity and omega is the angular velocity. And then you can do the whole multiplication to get something like. But in my opinion, this is just a conversion of units. A revolution is a unit of measure. Seconds, a unit of measure. Miles, right? Unit of measure. Hours, unit of measure. It's a rate. This is a rate. We can do just a conversion. It's all of your conversions of any kind of units are based on multiplication and division. And that's all this is going to have you doing too. So it all works together. It's all multiplication and division. So we start with what we have. 23 revolutions over 1 second. That's what I have right now. I'm going to multiply by something that's going to take away revolutions. So I'm going to put 1 revolution down here. So to do that would take away the revolution unit. But I can only do this if I put something up here that's equal to 1 revolution. Well, let's think about it. I'd like to convert it into something that is related to miles. Okay, well, if a wheel goes all the way around, that would be a circumference, wouldn't it? So up here, if I were to just say 1 revolution is equal to 1 circumference, right? 1 circumference is equal to 1 revolution. Well, but what would a circumference be if the wheel is, of course, perfectly round, which we're assuming it is? Well, a circumference is 2 times pi times the radius. Okay, so 2 pi, and it said my radius was 12 inches. So I've just converted revolutions into inches. And I want you to notice something real quick. 2 pi is an amount of rotation, and 12 is a radius. So notice omega times r, right? It's already built in, you see. 1 circumference is 1 revolution, and a circumference is just 2 times pi times radius. Right now, I am now in inches per second. I don't want inches per second. I want miles per hour. So 2 more conversions left to go. I'm going to convert inches into miles and seconds into hours. Okay, so a couple more multiplications. There are 63,360 inches in 1 mile. Now I've gotten rid of the inches. And seconds, I have 3,600 seconds is equal to 1 hour. Notice now there's a second in the bottom and a seconds in the top. And I'm very strategically placing these things. I want you to notice, if I want to get rid of something, I'm putting its similar measurement in the opposite type of spot, right? Here, seconds was in the denominator. So over here, I put seconds in the numerator. And then I made it fit appropriately, right? 3,600 seconds is 1 hour. And I put the seconds in the top so that it would wipe out with the other seconds. Okay, so notice the only thing left is miles and hours. And then I just need to do all of these calculations. 23 times 2 pi times 12 times 3,600. And then divided by, those are all ones, divided by 63,360. So in my calculator, this is exactly what I'm going to type. 23 times 2 times pi times 12 times 3,600 divide by 63,360. That's what I'm going to type in. 23 times, times 3,600 divided by 63,360. 98.53. So around 98.5 miles per hour. The last two problems from this test are using right triangle trigonometry to find some missing measurements. At the top of a 28-foot tower, you have a guy looking up towards a skydiver, and he measures from his horizontal the angle of elevation. Remember, angle of elevation and depression are all about measures from a horizontal of the person seeing it, right? So he's looking, his horizontal is here, angle of elevation up to the skydiver is 34 degrees 10 minutes. Okay? Now, don't forget the 10 minutes part. That's part of a degree. Okay? You see the little tick mark there is 10 minutes. We can put that in our calculator, or we can convert it by putting 10 over 60 if you want. Whatever way makes easier for you to punch it up. Okay, but anyway, 34 degrees, 10 minutes, angle up towards the guy. Okay, now the tower is 196 yards from the spot he's going to land. Okay, they want to know how high up at that moment is the skydiver when he sees him at that particular angle of elevation. Okay, so let's put a couple of things down here first. He's on the tower, right? The guy's right here on the tower, and he sees the skydiver up in the air from his horizontal. That's this angle right here. So that's the 34 degrees 10 minutes right here from his horizontal. Now, give or take that, you know, we're not counting the height of the person here. Okay, he's 28 feet in the air. Don't forget, the landing pad is over here, right? It's on the ground. So we still have another 28 feet here between the guy's horizontal that he's seeing, right, and up to from the ground up. Okay? So what we need to know is, what is this amount over here? Okay? So my skydiver's right here. Okay? I'm going to call this X right here. This little distance. This is going to be a right triangle because he's falling vertically and we're measuring it from a horizontal. They say that the horizontal distance here is 196 yards. Okay? Well, but I need everything in feet. It says to the nearest foot. So I'm going to do 196 times 3, because there's 3 feet in every yard. 588. Okay, and that's the measurement along the bottom of the triangle there. So notice, I need to know this height, and I know this length here, and I know the angle. So that's the adjacent and the opposite side to that angle. So I'm going to set up tangent of 34 degrees 10 minutes is equal to X divided by 588. I'm going to multiply both sides by 588, so X is equal to 588 times the tangent 34 degrees 10 minutes. So X is approximately, and then this is where we got to punch it in. Now remember, you can punch it in like this in your calculator, or you could do 34 plus 10 sixtieths, right? 10 over 60. I'm going to punch it in using the degree and minutes that you can use the degree and minute button here. So I have 588 tangent 34 degrees 10 minutes. Okay, so there's the tangent. The 588's next to it. And I'm going to hit enter here. I'm getting 399.1. Since they said rounding to the nearest foot, I'm going to say that this is around 399 feet. Okay? And then he's still got the other 28 feet to finish falling. So the answer to the question is I'm going to add that 28 feet on top of it right there. So I've got 427 feet off of the ground, the skydiver is, total. Next. This one is one of those nested type of problems. We have a same idea with a spotter and looking at things up at an angle of elevation, but it's something that's already in the air. The balloon's already there, and the balloon is rising. Okay, so the guy's looking out to the balloon, and then he sees it go up. He measures the angle of elevation where it began, and he measures the angle of elevation where it stopped rising. So we have this situation where we have the difference between two triangles that are nested into each other. So in other words, I've got the spotter on the ground, right? And he is 47 meters away from a launch pad that goes straight up to our balloon, right? But then the balloon also chooses to rise up a little bit more. So he sees it the first time at one angle, and then he sees it a second time at another angle. So notice I've got the small right triangle here, and I've got the larger right triangle here. Okay? So let me finish labeling the angles here. I've got that this angle right here is the 27 degrees 43 minutes. And we have this angle right here, right, all the way from the bottom, both of them are from the horizontal of the person, is the 53 degrees 19 minutes. Okay, now remember, don't forget your minutes along with these things too. That's part of the accuracy of the measurement of the angle. So then what I'm going to do is I'm going to label this little piece right here y, okay, from here to here. And I'm going to label this piece right here x. So what I've got is two triangles here. I've got the smaller triangle that just has y. It has the 47 meters here. And then it's got the 27 degrees 43 minute angle. And I've also got the larger right triangle, which on the other side, on the bottom side, still has the 47 meters. It's measuring the angle 53 degrees 19 minutes. But then this side over here is both of these put together. So this is x plus y. So what I need to do is I need to find x, and wants to know how much did the balloon rise just in that small amount of time. Well, I just want x. So what I do is I figure out what y is first using our normal right triangle stuff, and then I can figure out x plus y. I can just subtract y off of that, and I'll have what x is. Okay, so let's start by finding out what y is. I can see that I have an angle with y as the opposite and 43 is the adjacent. So then I have tangent of 27 degrees 43 minutes is equal to y over 47. Therefore, y is going to be equal to 47 times the tangent of 27 degrees 43 minutes. Okay, I'm going to leave that right there for accuracy purposes. I don't really need to know what y is yet. I just need to have a way of calculating it so that I can use it in the next bit. Okay? So now I have the tangent. Notice it's still opposite and adjacent. The tangent of 53 degrees 19 minutes is equal to x plus y over 47. So again, I multiply both sides by the 47. And I have x plus y is equal to 47 times that tangent. I'm interested in x, so I'm going to subtract y from both sides. But instead of y, I'm going to write this. So here's what we get. We get that x is equal to 47 times tangent of 53 degrees 19 minutes, right? That's this, minus y. So minus, this is y right here. 47 tangent of 27 degrees 43 minutes. And then I can compute what that is approximately equal to. Let's do that. I'm going to have 47 tangent 53 degrees 19 minutes minus 47 tangent 27 degrees 43 minutes. And I'm getting 38.400 on that one. Uh, 4006. Yeah, is what I'm getting there. Okay. Now remember, the 47 was in meters, so this is meters. It asked for the nearest centimeter. Okay. So x is approximately, and I'm going to convert this into centimeters, 3840.06 centimeters. So therefore, the nearest centimeter, right, is going to be the 3,840. There's our final answer in centimeters right there. Double check if I typed that in right. 27 degrees, 43 minutes. Yep. Okay, so I hope these problems have given you something else to practice and some insight into the skills that you need to practice to be ready for a typical first test in this kind of course in trigonometry.